This is a proton, and when they bond together, it'd probably be something kind of like this. And these form shells now. Some say lithium, I think 11, has a halo where they start getting some of these orbiting outside the inner part of the nucleus. So, to use balloons to learn this, what's more massive? Can you see it there? 2 greens and the red is more massive than the 2 reds and 1 green. So again, there's your neutron. There's your proton, come together with 6 gluons to hold it together by transmitting actually a pion particle through through the gluons. So this is what a deuterium, a heavy hydrogen nucleus, would look like. These quarks are going to be spinning around super fast. There's even a heavy tritium, they call it. That would be 2 neutrons and 1 proton. So there's 3 types of hydrogen that you need to know. 99 point, I don't know, something, is always just going to be 1 proton by itself. Then another percentage is going to be 1 proton, 1 neutron, and even a smaller, teenier percentage is going to be tritium with 2 neutrons, 1 proton. So this first atom, hydrogen, you can learn everything you need to know about how bigger atoms are made. Proton needs the neutron. Now you can have 2 protons and 1 neutron. That's what actually happens here. When you have a deuterium in the sun again, there's a whole bunch of protons running around, right? Running around, flying around at high speeds in a plasma state. So you bring another proton to hit this deuterium. Now that it's got 2 protons, that's going to make it a helium. You see the way the name of the atom changes, so you got to know protons from neutrons. The proton determines the chemical nature of it, because that'll hold an electron. A neutron is neutral, right? Electron has the electromagnetic force, so the neutron doesn't attract any electrons, only the proton. So 1 proton with 1 electron is a hydrogen. Doesn't matter how many neutrons you have, it's still hydrogen. But now, if you bring another proton in, you have 2 protons, 1 neutron. That's a helium-3. Helium with the 2 protons. And then finally, that's not even stable yet either. Then they say 2 of these come together, kick out 2 protons, and you end up with the alpha particle. That's the real stable neutron, neutron, proton, proton. 2, 2. It's magic numbers, they call them. I'm going to have to make another neutron here because I lost my blue one. So nuclear balloon chemistry here. This is what the helium-4 alpha particle would look like. 2 neutrons, 2 protons. So we went from the quarks. Now we're going to let 1 red one, instead of being an up quark, 1 red is going to be a whole hydrogen atom. 2 ups and a down quark. So 2 hydrogens won't stick together. You at least need a neutron in there. This is deuterium. Oh, it's got a hole in it. That's tritium. 2 neutrons, 1 proton. 2 protons, 2 neutrons, that's the alpha particle. That's our next phase that we need to go into how bigger elements are made. So, study this plate for a little bit, the proton-proton chain. Our sun is making this now. It's new mass. It's making big neutrons from protons. They call it fusion. They call it heavy hydrogen. It'll be written 1 with a 2 next to the H. And all this comes from, if you get this, because this isn't in the books. Every astronomy magazine once a year has a whole thing on quarks, and they draw the quarks the same size, and know it. Bigger down. So an up quark goes to a down, to a positron, and to a neutrino. And the way that the electromagnetic charge is 2/3 goes to being neutral is the up goes to a down, and a whole charge is taken from that up. The positive charge goes with the positron. So you're left with then a negative 1/3 for a down quark. And the neutrino is no electromagnetic charge. They say it's massless, but it's going to turn out, I think they're going to find to have a little bit of teeny mass. So draw the neutron bunny here. It's got the quark, the gluons and the quarks, the color for electromagnetics, and the size for the mass. Neutrons, I did this with high schools. I go to some of the fanciest high schools in the country. Ask the honors chemistry class, what's bigger, a proton or a neutron? Half the class says a proton. So now you know from drawing this what the nucleus is going to look like. Our sun right now making neutrons that eventually makes it into helium. So that's why they say the next thing after it uses up most of the hydrogen is going to go to fueling heliums, the alpha particles. So that's what we're going to show you now. All right, look this over for a second here, because 1 neutron, 2 protons is a helium-3. 3 means a mass of 3. Helium has to have 2 protons, so the other mass must be a neutron. Well, their model that they show, the astronomers, cosmologists, is 2 of these coming together. They fuse to make a helium-4. So it's going to have to kick out still 2 protons, so it's the equivalent of just another neutron adding there. So that would be two protons, 1 neutron. That's a helium-3. So 2 of these come together, and what the equivalent is another neutron. So this is what the alpha 4, this is really stable now. What you find alpha decay, big elements like uranium and that, they'll kick alpha particles out. This is what the old Rutherford experiment was an alpha emitter shooting at a sheet of gold foil. So big, massive alpha particles shooting out, hit a gold atom and bounced back at them. They were able to detect it. So alpha particles now. This is our next building block. The Greek letter alpha looks just like a fish, right? So what's neat now, again, see, this is just the nucleus. Inside a star, it's too hot for the electrons to exist yet. So the alpha particle and another alpha particle come together. They won't bond. They'll stick for the split second in what's called beryllium-8 excited state. That's what this little asterisk means up there. So when 2 alpha particles come together, if a third one comes quick enough before it decays back to 2 separate neutrons, before one of those takes off, 3 of them come together. That forms a stable carbon-12. So the way I see it is, alpha is a fish now, right? So the fishes started coming together. 3 little fishies swimming in a sea. Get it? C for carbon. 3 alpha particles in the nucleus. Remember, if there's any electrons involved, they're going to be way out there. For carbon, for example, you'll have 2 electrons in the first shell and then 4 in the outer. Then it'll need 4 more to fill that octet of electrons. But this is all in the nucleus. Alpha fishies. 3 little fishies swimming in a sea. Carbon. Tell me a little kid can't get this. So what happens if you added another? Say now you have four alpha particles. It's going to make an oxygen 16. So you see now the alpha particles are the building blocks. Another alpha, get 5 of those in there. Neon 20. So this is where the red stars, if you remember my little thing about C star here, C star used to wear a Cincinnati Reds hat, C for carbon. It's red stars. People tell you, oh, red stars, red is low energy. Well, that's the atmosphere. They're still hot inside. 10 times as hot as our sun, a little less, 100 million degrees. Our sun is about 15 million degrees in the core. 100 million degrees is what it will take to start fusing the heliums. No more quark changes. Remember, the first step was making the neutrons. So this is a whole different star now. This star isn't making neutrons anymore. Now it's actually fusing, sticking stuff together. I don't like the term that our sun is fusing hydrogen because it's changing quarks. It's changing an up quark to a down. It's making mass. I don't call that fusion. They should come up with a different term. This is actually fusion because these alpha fishies are coming together. Consider the nucleus like a little school of fish. 2 fishes don't work. If 2 come together and a third comes, then you got a carbon 12. That'll stick. Add another one, 4 alphas, oxygen 16. Add another alpha, neon 20. So this is what's going to be happening in the core of red stars around 100 million degrees. Higher temperatures will start fusing carbons together, silicons together, bigger elements. But for all general purposes now, alpha particles, that's the building block. Previously, the building block was neutrons. Previous to that, the building block was the quarks, the 2 ups, 1 down for the proton. So see, you got to learn the terminology. That's what loses everybody. What is hydrogen? Well, are you talking the quarks? Are you talking the proton? Are you talking a proton and a neutron? Are you talking a proton and 2 neutrons? Are you talking the proton, 2 neutrons, and the electron? Because technically, they'll call it a hydrogen, but it's not a hydrogen unless there's an electron involved. So you've got to really technically call them protons. Until it's in a chemical, which means electron is involved, a chemical atmosphere, it's not a hydrogen atom. It's just a nucleus. And the nucleus could be just a proton by itself. So when they say all this hydrogen is out in space, some is bound as H2 in a molecule that needs electrons. Some of it is just free-floating protons. So again, if you can learn this phase, red stars fusing the positive, that's why I keep this red, because these helium nuclei, the alpha particles, they get a +2 charge overall because there's no electrons to balance it out yet. 2 protons, the 2 neutrons, give it a 2+ charge overall. So I'll hold that there. You can pause it, freeze frame. Learn this, kids. I had to learn it myself because it's not in the books. And if you know it, then you'll be able to understand the books. If you try and memorize what the books have about chemistry, even if you pass a test, you don't really know it. Quarks go to make neutrons. Protons, neutrons go to make alpha particles. Alpha fishies go on to make bigger elements. And conversely, alphas are how the big, gigantic elements decay. Alpha decay. Alpha emitters, they'll call them.